All right. Thank you, everyone. Welcome. Thank you for coming. Just a quick intro for myself and Otters before we get to our incredible speaker for today. So I'm Josh Strauss, a doctoral candidate at UMD's psychology department and the speaker series coordinator for this year's Otters Speaker Series. Otters is the Organizational Teams and Technology Research Society, a network of scholars across the DC area dedicated to researching and learning anything and everything to do with teams and technology. It is my pleasure to introduce our speaker for today, Dr. Nancy Cooke, a professor of human systems engineering and an affiliate professor of bioinformatics and a senior scientific advisor for the Center of Human AI and Robot Teaming at Arizona State University. She is also the chair of the William C. Howell Young Investigator Award for the Human Factors and Ergonomics Society, which also selected her as the HFES Titan to speak at their 2022 symposium. I won't go on to her other accolades because that could take a while. Her research revolves around socio-technical systems in high-stakes contexts, such as remotely piloted aircraft systems and healthcare systems, and includes topics such as human AI teaming and my personal favorite, individual and team cognition. So with that, I will say, please hold questions till the end, unless they are clarification questions, in which case, please just send them in the chat, and I will interrupt and read them off as they come up. So without further ado, everybody, Dr. Nancy Cooke.
Thank you very much for that really nice introduction, Josh. I'm glad to be here. Thank you for inviting me to talk to you. I'm really passionate about this topic. I love talking about it. So I'm going to talk about interactive team cognition for humans and machines. Just to check that you can hear me and see my slides. Yes. Okay. So I've been doing this for a very long time, and I'm going to talk today about what's transpired after 30 years of research on team cognition, some discoveries we've made along the way. And when I say we, I mean we, because there's been a very large group of students and their faculty that have been with me along this journey. So talk about the importance of team interaction, improving teamwork through perturbations, and what it takes to be a good team player and the power of a single teammate, and then close with some promises of what's to come in team cognition. So I studied team cognition in socio-technical systems, and that means systems with lots of technology and lots of people. And the whole goal is to improve team effectiveness. In order to improve team effectiveness, though, you have to be able to measure team effectiveness. And so that's been a very large part of my research. And to do that, we have made heavy use in our research of synthetic task environments. And I call this the living lab approach. That the important thing about it, I think, is that the research and the development of a synthetic task environment begins and ends in field. And so we take cognitive task analysis, for instance, in the field, and we develop based on that. We abstract that in the lab and develop synthetic test beds. We then collect data in those test beds, develop measures in those test beds, and from that comes models and theories of teamwork. And then the idea that we take those results and they end up back in the field, hopefully. And that's the part that's probably the weakest, is transitioning things back into the field. And we've had, over the course of these years, many synthetic test beds. Some of them, thanks to COVID, have been virtual. We've made heavy use of Minecraft recently to do urban search and rescue kinds of environments where people can use their avatars to work together as a team. We have some physical test beds, and I'll talk pretty extensively about our remotely piloted aircraft system synthetic task environment, Uh, I'll tell you about that more in a minute, but we also have generic team decision-making environments. We have Chartopolis, which is a scaled down city where we can have driverless vehicles drive around with remotely driven vehicles to look at the interactions between driverless vehicles and human-driven vehicles. We also have Minecraft-based next generation combat vehicle simulations where you have manned tanks preceded by unmanned tanks. And our newest synthetic task environment is called the Ghost Lab, and we have full-up robots in there, a Husky, a Yumi, and a Fetch, some swarm robots. And it's been developed also in conjunction with Dr. Lance Scaravi, who's a theater professor, and we have full-up theatrical sound and lighting so that we can change the environment of the lab to make it the surface of Mars or maybe underwater, and carry out scenarios in that lab where people are interacting with robots, and they can interact in any way that we tell them to interact, including natural language, because we operate the robot's Wizard of Oz from behind the wall of the room. So those are the test beds that we use. And let me turn now to the remotely piloted aircraft system research test bed. This was based years ago. It was the first test bed we developed on Predator operations. And in this task, we have 3 operators who have to coordinate over headsets or text chat to maneuver a vehicle to take pictures of ground targets. And these are the 3 operators. There's the payload operator, basically the photographer, the air vehicle operator or the pilot, and the navigator or mission planner. It's called DEMPSI, and it's that is an acronym, Data Exploitation and Mission Planning Coordinator. This task is a great team task, and we've collected lots of data and done lots of experiments with this task because it's very interdependent. You can't do this with one person. It requires interaction, communication, and coordination. And by coordination, I mean, it's the time, it's not just what you say, it's when you say it and who you say it to. Okay, Discovery 1, and this is about as fancy as my animation gets. The importance of team interaction. One of the first experiments that we did in that RPA lab is on team skill acquisition. And so we had a series of 10 missions, and we're looking at each line represents a different 3-person team. And on the y-axis, we're looking at a team performance measure, which basically starts at like 900, and you lose points for going through threatening waypoints or for using lots of fuel or not getting good pictures, for instance. Individuals are trained to criterion prior to mission 1. So they each know how to do their own job of being either the pilot photographer or mission planner. They reach asymptotic performance in 4 40-minute missions. And this is a pretty robust finding across almost all of our experiments. And so this really represents team learning. So what's happening? And as I said, they were trained on their task prior to mission 1. So you might think, well, they might be learning about other team members' tasks. And we looked at that. We measured their knowledge before and after, and it didn't really change much. But what was changing was their team process, how they were communicating, who they were communicating to. They were learning, what do I need to do for this team? What information do I have that other team members need? And that was what was really changing. And so this told us that, well, these interactions that are happening in the beginning are pretty important. And everybody always asks about what happened at mission 8 to that one team. You see, they all took a little bit of a dip there. That, let me see if I have it. That was spring break. We didn't do all these sessions in one, all together in one day. So sometimes they were separated by days or even weeks. And it took people a while to come back after spring break. And so teams learn, teams also forget. I don't know what happened to that one team. They did pretty poorly. I don't even know if they were all there. But I say this is maybe an argument against spring break, but I'd hate to say that. Now, these results and a lot more results like that led us to develop the theory of interactive team cognition. And it's pretty basic. It says that interactions are important. Team interactions in the form of explicit communications, sometimes but not always, are the foundation of team cognition. And we see team cognition as an activity, not a property or a product, that is tied inextricably to context, and it's best measured and studied when the team is the unit of analysis. And I'm going to contrast that to what at that time was the prevailing approach of shared cognition that says that team cognition is the collective knowledge of team members. So we take the knowledge that each team member has and we can aggregate it. In this case, the individual is the unit of analysis. We measure it at the individual level and aggregate, and that we assume that the more similar knowledge becomes over time, that means teamwork will be better. The focus is really on pretty static knowledge, a snapshot of knowledge at one time, and it assumes that a collection of knowledge experts should be an expert team. We saw that not only were we finding that these interactions were important and that knowledge wasn't really changing like you would think with shared cognition, but that the empirical evidence was mixed. Also, we thought there's some logical or pragmatic limits to thinking about shared cognition in this way, that the idea that you can aggregate knowledge kind of goes against the idea that teams are heterogeneous. So you think about aggregating the knowledge of a nurse, a surgeon, and an anesthesiologist. It's like aggregating apples and oranges. And really, should that knowledge start converging? Probably not. I mean, there's some things that they probably share, like what leg they're operating on, but it's not that they have the same body of knowledge. And also, it doesn't scale well to larger teams as teams get larger and more diverse. I mean, the whole reason we need teams is that we have people who have different roles and responsibilities and they bring different knowledge to the table. So the focus on static knowledge also misses the fact that knowledge and team knowledge will change. It misses the dynamics. There's some assumption that the cognitive whole is the sum of the parts. And so this didn't make sense to us. And I like talking about these examples because I think they drive this home. This is the 2004 Olympic basketball team that was made up of very stellar basketball players. They were professionals. They were all superstars in their own right. And they came to the Olympics and went on to lose miserably. And this is a quote from the head coach, Larry Brown. He has a good understanding of who needs to play. Now the job is to get an understanding of how we have to play. And there's a lot of speculation that they just never really worked on that glue that would hold them together. They never practiced. They didn't practice together enough. And so they were each kind of working as individual stovepipes. This suggests that collaborative skill is not additive. A collection of experts doesn't necessarily make an expert team. Contrast that to the 1980 Olympic ice hockey team. And if you haven't seen it, I encourage you to see the movie Miracle on Ice. It's about this team. This was a team made up of college hockey players. They weren't professional, and they called them young no-names. And they went on to beat the Russian team, and they were the underdogs in the 1980 Olympics. And it was, the movie's great, and the movie portrays the coach as being really good at these interactions. And so he would have them run drills across the rink every night, and they became kind of cohesive in their hatred of him. That he did in-group, out-group kind of things where he brought in strange players, and they also became more cohesive, but they practiced a lot, practiced together, and really worked on that teamwork. And so to me, that's what makes a good team. Now, when you think about team cognition in terms of interactions instead of static knowledge, it suggests some different ways of looking at things. So different ways of maybe training teams to be adaptive. I'll talk about that in just a minute. It suggests different maybe technological interventions for improving team performance. Maybe your display for team situation awareness would look different. When you go into command and control centers in the military, they have just a whole wall of data of screens that show everything from CNN to maps of the world. And you ask them what that is, and they say, that's our situation awareness. I'm like, well, and they, how is that your situation awareness? Because it would be impossible to find what you needed in a timely manner. And in fact, people don't tend to look at those displays at all, because what you need for team situation awareness is getting the right information to the right person at the right time. And that data wall is kind of based on the idea that everybody has to know everything. It suggests two metrics of communication and coordination that could be used to monitor just-in-time and do just-in-time interventions. We've made extensive use of interactions in terms of measuring team cognition. And they can also, these metrics can facilitate human systems integration because we can apply these metrics not just to humans, but also to machines and technology. And we can use them to have an ongoing assessment of the system state. Okay, so that was the importance of interactions. And now I'm going to talk about, we found out that we could improve teamwork through what we call perturbations or roadblocks or system failures. This was an experiment we did also in the RPA testbed, in which we had 117 participants divided into 39 three-person teams. We had we manipulated two things: retention intervals. So this is kind of an intentional manipulation of the spring break effect. We had some participants came back 3 to 5 weeks later, others came back 10 to 13 weeks later. We expected that there'd be more forgetting 10 to 13 weeks later. And spoiler alert, that's exactly what happened. But the interesting thing that we manipulated is what the Air Force wanted us to manipulate for quite some time. It was kind of logistically a nightmare, but we had teams that were intact or the same. And those were teams that they were in session 1 together, same individuals. They were all same role in session 2. In the mixed condition, that's where we mixed up the team. So if I was an air vehicle operator in session 1, working with a PLO and Dempsey, I'd come back still as an air vehicle operator in session 2, but I'd be with a new person PLO, a new person Dempsey. This was logistically difficult because not only did you have to get these 3 people to come back at precisely to come back together in these specific intervals, but they had to come back with the right people. So it had some of my experimenters in tears, but we pulled it off. And let me show you what happened. So this is what happened for team performance. And again, it's a composite score based on getting good pictures and not violating any of the rules. And if you look at session 1, everybody is, again, acquiring that interaction-based knowledge in the beginning. And then in session 2, where they were in these different conditions, we see everybody but the short intact teams had some forgetting. And they also got back up to speed by mission 7. So that was not unexpected. But here's something that was unexpected. It was a different story for team process. In team process, we measure in a lot of different ways in terms of their interactions, their communications. We have experimenter observations of team process behaviors. And no matter how we measured it, team process improved over the first 4 missions. And then for the intact teams, and this was unexpected, the intact teams kind of flatlined, where we expected, and I think the Air Force expected, that teams who stay together would have better teamwork than teams who are newly mixed. But that wasn't the case. The newly mixed teams, there were different people now. They kept improving in process and kept doing well, especially when we had novel events. And we reasoned that this was probably because it was because we looked at the data that they were learning how to do the same thing in a slightly different way because there was a new PLO in Dempsey who had maybe from their previous team had slightly different ways of doing the same task. It gave them a richer repertoire of interaction techniques. This we also used these results to develop what we call perturbation training. So we reasoned that, well, do you have to mix teams up in order to get this increase in ability to adapt? And we thought, well, maybe you just have to prevent them from doing the task in the same old way. And we would do that by perturbations. And a perturbation would be like to cut communication between two of the people, forcing them to work around, or something would break on somebody's display and they'd have to get information from somebody else. So doing the same task in a slightly different way. That was perturbation training. We had in this particular experiment 3 conditions. One was knowledge-based training or cross-training. This is what you would, if you believed in shared cognition, you would think that if you cross-train people on each other's task, they would do better because they have more shared cognition. We compared that to procedural training, which was very, very rigid. You do it this way. If you don't do it this way, we're going to stop you. So this is kind of what happens when teams get in a rut. We found that there is definitely a disadvantage for procedural training, especially for very difficult or novel missions. And there was, in fact, a perturbed advantage over cross-training, over knowledge-based training. Again, supporting the idea that these interactions that are important and the extent to which you can develop different interaction strategies, you can be more adaptive. Okay, now, and this is going to be moving more towards technology, what does it take to be a good team player? This is our synthetic teammate experiment in which we worked with Air Force Research Lab, Chris Myers and company, who developed a synthetic air vehicle operator to sit in the pilot's seat. And this was based on ACT-R cognitive modeling. So the synthetic teammate knew how to do the pilot task. And we put it with 2 humans, the photographer and the mission planner. And in this particular experiment, we had 3 conditions. The control teams were our typical naive human teams, 3 people. The synthetic teams were 2 people and the synthetic teammate. The experimenter teams were also 3 people, but in the pilot seat, we had an experimenter who knew this task inside and out, who was able to kind of coach coordination subtly by demonstrating how, by pulling information when it wasn't coming at the right time. So we measured what we typically measure. We measure a lot: team performance, team process, and workload. And here are the results. So if we look at just team performance based on our composite measure, the synthetic and control teams were statistically equivalent. The experimenter team was much better. And there were some changes over missions. But here's what we found for target processing efficiency. And this was a measure that was developed to look at that coordination that needs to happen. So when you get to a target waypoint, the photographer needs to take a picture and needs to set the camera settings according to airspeed and altitude of the UAV. And the mission planner has to be able to provide information about altitude and speed restrictions to the air vehicle operator. All of that information gets passed in hopefully a timely manner so that when you get to the target waypoint, the photographer is ready to snap a picture. So this target performance score is how fast you get in and out of a target waypoint with a good picture. And what was really, there are several things that are interesting here, but the synthetic teams were the poorest at target processing efficiency, and the experimenter teams were the best. What was even more interesting was that the synthetic teams seemed to decline over time. And what was happening is that the synthetic teammate, although it knew how to be a good pilot, it didn't really understand the team part of this task. So when people are in this task, they will anticipate, well, after those first 40-minute missions, they'll anticipate the information needs of their fellow teammates. So I know you're going to need to know what airspeed and altitude is going to be when we get to the target, so I'm going to give it to you now. The synthetic teammate didn't do that. It just waited to be asked for that information. And as a result, coordination suffered. But what was interesting is that the two naive humans entrained to the messed up synthetic teammate. And so they stopped sharing information as well, or anticipating information needs. And so that's why their coordination just got worse and worse. Everybody was just waiting to be asked, and they weren't very proactive. I had a student, Mustafa Demir, who did his dissertation in 2017 and found that coordination is pretty important and also pretty interesting. He looked at dynamics of the coordination and looked at a stability measure and found that the best team performance had this kind of sweet spot of meta-stability, that you're not overly rigid like the synthetic teams, but you're not more chaotic like the control teams. So as you get to be better and better at this task, you have the ability to be stable when you need to, but also to flex when novel things happen. It's kind of like a good bridge. You're stable in the long run, but you're also able to flex when needed. And so what does it take to be a good teammate? I think we found that it's meaningful communication at the right time, anticipating needs of fellow teammates, being proactive in response to the task and to the team, and being flexible in the face of change. But then there's this interesting problem of entrainment that we found, and more on that later. Okay, coordination coaching, or the power of a single teammate. If you remember, these are the target processing efficiency scores, and we found that efficiency was poor for the synthetic and control teams, but it was very good for the experimenter teams. So that study told us that subtle coaching of coordination by the trained experimenter can also improve team performance. I had another PhD student, Sandra Hinsky, who applied this coordination coaching idea to Code Blue resuscitation at the Mayo Clinic. It's a mock Code Blue. And she was a respiratory therapist by training. And she was interested in the kinds of errors that teams make in Code Blue resuscitation. They are led by an intensivist usually, but what she did was to prepare a communication model for the code leaders to study ahead of time. These are doctors at the Mayo Clinic, so it was hard to get too many of them, and they claimed that they looked at this model for 5 to 10 minutes. But the whole idea here is that if the information isn't coming when it should be coming, you pulled the information. And so if the code nurse doesn't immediately give the code leader a brief history, code status, and confirm advanced monitoring established, then ask the nurse for that information. And so when they did that, we looked at control groups that didn't have that model for training versus groups that were trained. And again, they said they read it for 5 or 10 minutes, but it had some really interesting results on the number of errors that the code team made. And I'll explain why we looked at these kinds of errors, but the errors about not identifying yourself or not being positioned properly, those were fewer in the case of the trained group than the not trained group. So this is not a whole lot of data here, but it does show that there's promise for this kind of coordination coaching. Okay, and here's some newer directions, and a lot of these new directions have to do with measurement. And so one is the meaningful assessment of team effectiveness. And we're really thinking about that lately. What does that mean? That part of the problem is that we've been using outcome in the lab, like how many good pictures did they get of targets? But we can't do that often. Most of the time, actually, outside of the lab, there's no ground truth. We don't know where the targets or what the targets are, where they are. If there's cyber threats, we don't know if they found them all. When we have synthetic task environments, we know that because we put the threats there. But we can't always measure outcome in the real world. Also, in the lab, effective teams usually do have positive outcomes, but outside the lab, there's not always a one-to-one mapping between outcome and team effectiveness. And in the code blue resuscitation, for instance, there really isn't. If you are the victim and you find yourself in a code blue resuscitation event in real life, it's not a good day. And there's about a 20% chance that you will walk out of the hospital. A little bit higher chance actually at the Mayo Clinic, and probably because their clientele, their customers are different. So if you lose a patient when they're undergoing code blue resuscitation, it does not always mean that the team was ineffective. And so we need some other way to measure it. Also in sports, if you ever watched a child's soccer game, you can tell sometimes they played a really good game, but they ended up losing, or they really, didn't play a very good game, but somehow miraculously they ended up winning. So there's not this one-to-one mapping, and the same is true for a lot of things. For team science, for instance, how do you measure an effective team doing science together? Right now, they tend to use bibliometrics, how many citations together and stuff like that, but it's not, that's not ideal. So we've been thinking about this and thinking, well, in our studies, the best teams that we see are teams that are adaptive to perturbations. They respond quickly, and they're also resilient. They won't let it throw them. They bounce back. And so we've been working on measuring team effectiveness through performance dynamics. We found that effective teams are adaptive and stable, as I mentioned before, like a good bridge. But if we could throw a perturbation at a team and measure how long it took them in terms of the dynamics to adapt, and then how long it took them in terms of the dynamics to go back to their resting spot, we could have an index of team effectiveness. And so we've been working on measuring resilience and even trust using team dynamics, but effectiveness is where we want to be. And a little bit more on this. We're trying to improve team measurement. And when we think about a whole system, like a system of like a military joint all domain command and control, where you have land, air, sea, cyber, all working together, lots of different machines, lots of different people, how would you measure the effectiveness of that system? What we've been working on is Jamie Gorman's layered dynamics approach, and Jamie Gorman is at ASU now. We take signals off of the system, and they could be human physiological signals, it could be communication signals, it could be vehicle positioning signals, and we apply layered dynamics. And you can see in layered dynamics when there's a perturbation that you could see how it kind of cascades through parts of the system. And in this way, you can even identify maybe unintended consequences of the system. Our next step, so we're still working on this. We have a space challenge project and an Army-based project where we're trying to measure teams in this way and translate it into a dashboard that could be easy for some commander or instructor to interpret in terms of the state of the system, state of the team. So we're going on to measure adaptation, resilience. We're trying to make it so that we could do this in real time as the team is in action, and to automate our measures. Although we've done lots and lots of communication analysis, we've hardly ever looked at content, because that's a good way to lose graduate students, having them do that content coding. But we do look at communication flow, who's talking to who, how much are they talking, things like that. So it can be automated. And then We want to extend this to larger teams and systems, which we're starting to do. And we thought one thing, in addition to the dashboard for the commander, you could have almost a dashboard for the team itself to kind of give them some feedback about how they're doing at the moment. Okay, now human AI robot teaming. So we've been doing a lot since the synthetic teammate was kind of our first step into that world. We've been doing a lot more since then. I think there's some controversy about whether AI or a robot can be a teammate. And to clarify what I mean by that, I think that there's a lot that we can take from the team literature, the human team literature on team composition and role assignment, even the definition of team, to inform human AI teaming. We can take different team processes that we know to be effective. How do they work then for human machine teams? How do we develop or train these teams? And how do we measure the effectiveness of these teams? But this is where it becomes controversial sometimes. When I say teaming and human machine teaming, I don't mean that the machines are in control. That's a whole other issue about who's the team leader or who's in control. It's orthogonal to the teaming issue. It doesn't mean that the machines are human or human-like. Some people say, well, I can't have a robot teammate because I wouldn't be taking it out to lunch, but taking it out to lunch isn't in the definition of team or teammate. And it doesn't mean that the machine is not human-centered. So I think that, in fact, if you design an AI system to work well as a teammate works, then you can increase the human-centeredness. So on to what does it mean to take teaming seriously in human machine teams? It means that team members have different roles and responsibilities. And taking this seriously means, for most cases, there's no reason that we need to replicate humans in AI or robots. There are maybe a few exceptions, such as for autistic or maybe elderly people, you might want to have a humanoid robot conversing. But for the most part, we should do what we do best and let the machines do what they do best. The other exception is in our synthetic teammate work. The reason that the Air Force wanted synthetic teammates is that they could use them for team training anytime, anywhere by just, I need my team training. I connect to the internet and work with synthetic agents to get my team training, rather than to have to assemble large numbers of people who don't need training just so you can get yours. I don't think that they've gotten there yet, but that was the goal. I think that I'm a heavy believer also the Centaur model, where it's like half human, half machine, where you're working together doing the same thing, like in the case of chess, doing the same thing, but in a very different way. The Centaur chess turned out to be a big success. The human is able to remember specific games, and the machine is able to look far ahead. So together they went on to beat Garry Kasparov, the best grandmaster, and also to beat the best chess program. I also think it means that teams understand that each member has different roles and responsibilities, and therefore you need to avoid role confusion, but back each other up as necessary. This is what the synthetic teammate didn't do. The autonomy of the machine needs to have an understanding of the whole task. And so what does that mean? How does it have an understanding of the whole task? And I think there's a lot that still has to be done in that area. Effective teams share knowledge about the team goals and the current situation that facilitates coordination and communication. And I think this suggests that so teams aren't good, human teams aren't good right out of the box. It took our teams in the RPA task for 40-minute missions. I don't think we should expect humans and AI to be any different, that there needs to be some time where the human learns about the capabilities of the AI learns about the capabilities of the human. A lot of this also has been drawn from studies of human and animal teaming. such as military working dogs or marine mammals who find ordnance under the sea. It's true that you'd have a trained handler and a trained dog, but together they wouldn't work well until they've spent some time together because they need to understand about the idiosyncrasies of each of them. So I think co-learning or co-training is going to be important. And effective teams have team members who are interdependent, so they need to interact, they need to communicate, even when direct communication isn't possible. And I think, we're putting a whole lot of weight in natural language now. I don't know that natural language is the way that we should be communicating with robots and AI. In the military, we use brevity code and signaling. And why do we do that? Well, natural language is sometimes ambiguous and we make mistakes. So that's why in air traffic control, they have specific ways that they're supposed to communicate. And back to dogs, we don't communicate. Well, some people might communicate with their dog in natural language, but usually it's one word utterances or signals. And the dog seems to understand what you want. The dog has a theory of behavior rather than theory of mind. It's studied your behavior. So maybe we should think about another model of communication with AI, with robots. And now interpersonal trust, it's very important in human autonomy teams. We know about the importance of explanation, but we need a lot more on that. How much do you explain? How much is enough? And should the AI be trusted? In our synthetic teammate experiment, in which the people entrained after the synthetic teammate, part of the problem was that they were new to this experiment. They were told they were working with AI. And so they decided that the AI should be trusted more than they should be. So if the AI is not being proactive, maybe they're not supposed to be either. So that was a case of overtrust. So all of this adds up to effective human-machine teaming for the future of work requires human systems integration. So tight integration of humans and the systems for human-machine teaming. And just to summarize, I just went into 4 discoveries over these 30 years. And there's more of them, but they didn't talk about. But right now we're working on a lot of measurement problems and of course, putting AI and robots on teams. And I mentioned that this was work that was done by a whole lot of students and other faculty. And this was taken during COVID times. And I think it's so interesting to look at their faces then. And once we came out of the pandemic, look how happy everybody seemed. This was like our first face-to-face meeting. And so I think that face-to-face teaming is happy teaming. So anyway, I will go ahead and stop there and take questions.
Yeah, thank you so much, Dr. Nancy Cooke. That wonderful talk. I have so many, but I'll leave it open to others first, get some questions in. And just for the sake of the recording, if you send your questions to the chat or the Q&A, I'll read them off just so we have it recorded, and then Dr. Cooke will answer. So.
I have a question for people. Is there anybody that thinks that AI cannot be a teammate, that it has to always be a tool?
It's usually a hot topic for this group. We have Ben Schneiderman says, yes, I believe that.
I would think Ben would, yeah.
We do have another question in the Q&A. I don't know if you had a more follow-up. Ben also says thanks and good to see your work again.
Thank you, Ben.
So I'll go to the other question, if that's all right.
Sure.
James Grant says, thanks so much. To what extent does a dynamical system perspective allow the heterogeneity of entities to be incorporated into explanations? By definition, dynamical systems only model the system and not the entities, which seems to effectively treat the entities as interchangeable, i.e., as long as the system behavior unfolds in a particular way, it doesn't matter who the entities are. For example, how does one model explain a whole being, the less or more than the sum of its parts, without considering how the parts behave? The layered dynamics perspective seems consistent with modeling the parts of a team system rather than the team system as a whole.
Okay, trying to parse all of that. So yes, we are measuring. So with the layered dynamics, we could take physiological measures off of individuals. We can take positioning data off of vehicles. And so we do look at those as individual components, and the layers are putting it together as the whole system. Jamie Gorman has also come up with some influence metrics that you could see how one individual, maybe in some communication analysis, is influencing, has more influence, or one component of the system has more influence on what happens maybe after a perturbation than another. So we can drill down, but in the end, it's a system effectiveness that we want to measure, that we want to try to improve.
We have another question from Luke Osterritter, who says, I was surprised by the finding of team tenure positively affecting team performance. I definitely would have figured transactive memory or otherwise meta knowledge of what the team can do would have been a bigger advantage. Do you have thoughts on how transactive memory fits into this?
Yeah, I mean, I think transactive memory is important, and that's one of the things that you learn as those first 4 missions. Who has what? Who knows what? What do I need? Who do I go to for this? And I think that that's part of the learning of interactions. Who do I need to interact with? It was interesting that the teams that stayed together didn't improve as well. But this was in the case of changes in the task or perturbations. And so what happens is that you become kind of rigid, and I'm going to do it this way. This is how we've always done it. And so when something changes, you just don't know how to deal with it. You can't use your old way. And it kind of throws you more than the teams that have had some experience being flexible.
I have actually just a brief follow-up to that before I read another question. Sounds sort of like, or would you agree with the statement that the benefit for transactive memory then is the procedural more than declarative knowledge? You're learning how to ask or how to find out where information is, but not just who has information. Would that be a good way to dichotomize that, or not dichotomize, but separate?
Yeah, so the procedural knowledge of, who do I have to go to in order to get that knowledge? And so, and in all of this, I'm not saying that the knowledge piece is not important. Of course, you have to know something about what you're doing. And, the nurse has to have certain knowledge in order to accomplish the task. I'm just saying that it's not knowledge similarity that makes a good team.
Absolutely, that makes a lot of sense. And Luke had a follow-up that also said that makes sense. Maybe it's also another explanation he has is the transactive memory became stale. They needed to update.
Yeah, stale transactive memory. I like that.
Another question coming in. Ben Schneiderman also asks, what is the role of incentives for team members in improving overall or individual performance?
Yeah, so in our experiments, of course, it's just finishing this experiment and getting my credit or payment. That is their incentive. And I agree that I think part of the issue, especially in doing team trust research, is that the incentives, the risk structure isn't really the same. So that teams that are out in the field have a lot of incentive to perform well. Sometimes it means saving their own lives. And therefore, issues of trust become really important. In the lab, some of these things aren't as important because we can't put people at that kind of risk, of course. We've tried to incentivize by having like competitions. You get the big prize if you are the highest scorer, but it's still not the same as being out there in the field. So I think incentives play a large role in team performance, especially out in the field.
And as a follow-up to that, it sounds like you've done stuff with financial incentives. And yes, what's the impact, relative impact of financial incentives versus fame or team member respect?
Yeah, so Ben, I haven't looked directly at that. That's an interesting question. I think it would depend on what kind of team task you're undertaking. So the science teams, I think the incentives are very different. It might be more for team member respect or fame. But I think in the military team tasks, the incentives are often life and death, not fame. But it would be interesting to look at that.
We also have a question from Susanna here. Where can I find publications for all these things? She's got your 2023 paper, but the point specifically of natural language versus brevity and effectiveness in communication. Yeah, where can we find all this wonderful information that you have?
To be clear, I haven't done really research on brevity versus signaling. I just know that that's what we do in the military or in aviation. And we do it for that reason, that it's fast, precise, and non-ambiguous. But I have done a little bit of work on text chat versus voice, and that's, I can share some of that with you if you like. I have my, people can feel free also to drop me an email, ncooke@asu.edu, and I can share articles or point you in the right direction.
Sounds good. And we can also, if it's all right with you, share that out. Just have your email in the post. Oh, and Suzanne has it in the chat. There we go. So one of my many questions, but so you mentioned a lot of contrast between your approach and shared mental models, which I adore. That's the sort of impetus for a lot of my research is why are we looking at things so statically, single type of content at a time, a lot of stuff like that. And so I was wondering, do you see compatibilities with shared mental models and that approach and your approach, or are they two separate paradigms, or is there a way to bridge the knowledge we've gained from shared mental models to your interactive approach?
Yeah, and I think other people, I think Nathan McNeese at Clemson has been thinking about this, and I've been thinking about it too. I think that part of why this interactive team cognition seems to work well for us is that we're studying action-oriented teams. And what's important is that there's a lot of interaction. They have to get information to the right people at the right time. There's a lot of heterogeneity. But on other teams, and I would say like maybe science teams or teams that are doing long-term mission planning, there may be a bigger role for shared mental models, and it may be, and so if you take different tasks, it may be more or less about interactions and more or less about shared mental models. I think that, part of it is this kind of tasks that we have been using in our experiments.
That's interesting. I've always thought of, I've been thinking around cognitive actions for planning teams, but that does make a lot of sense that if they have to come up with a cohesive plan, they need to have more knowledge in common versus getting that when they need it. Yeah, that makes a lot of sense. Thank you. And we do have about 3 minutes. If anyone else has anything else to ask.
Well, these are all really good questions. Thank you so much for having me. I've learned a lot by just addressing these questions, and please feel free to drop me an email.
Well, so yeah, thank you, everyone. We have a comment rather than a question from Susanna. She says, I feel like one could do a study where the best teams researchers are especially good at attributing to their work students. Sorry, I think I misread. I feel like one could do a study where the best teams researchers are especially good at attributing their work to student teams, their great work. I'm sorry, I'm missing the slashes, throwing off my wording.
Yeah, sometimes we don't practice what we preach. And so I have been a member of teams that aren't so good, but my student team is the best.
Yeah, that's just clarified that people only attribute some success to themselves versus their students, which you're clearly in the latter camp. Sharing that recognition. I also actually, that gives me one final question before I close out here. What you said about the AI guiding people's behavior. I study teams because in part, a reaction to the intense sort of reverence for leadership. I want to know what the role of leadership is in the team rather than this higher up thing that, comes down into the team. Would you say that demonstration that you mentioned of that, yeah, setting the trend and people following, if someone has influence, that is maybe their most important role in a team?
So in that case, I think you're talking about the synthetic teammate that had influence in a bad way, though, right?
Yes. Yeah.
So yeah, they went along with the synthetic teammate because they believed that it was AI and it could do anything. And I don't think that that's unusual. In a lot of our experiments where we tell people they're interacting with AI, they treat it differently. We had a person once standing in for AI, an unknowing person. We told two people that they were working with AI, and they just gave that person commands. They left it out of the conversation. So I think that the way people interact with when they think something is AI is very different.
That's true. Yeah. Okay, well, on that note, thank you again, Dr. Nancy Cooke, and thank you everyone for coming out. Please check out our website, which I will put in the chat right now to see upcoming events. This was our last talk for this semester, but we have much more coming up next year. And so here is that link. And thank you all. We hope to see you around, Otters, again.
Thank you.